Okay, let's get started. So I want to let you know that next semester I'm teaching Calc 1. I've sent out a couple emails, but I've been meaning to tell you verbally. So it's Tuesday, Thursday, 9 a.m. It's 19669. Okay? That is 270. 270 will fulfill any requirement of any Calc 1 class that you could need. Most of you need 265. 270 trumps that, right? So it takes care of that requirement and will prepare you for your future math courses, your future engineering courses, as well as MA 265. So, and we'll be approaching the course very much like what this semester has been like. So, going on to Calc 1, you've enjoyed this. Join me, okay? Love to see you, okay? So, what are we talking about? We were tracking the position of the bug, and we were looking at horizontal position of the bug. So let's really define our input and output quantities really specifically to start here. So specifically, what was the input quantity we were looking at if we wanted to track the horizontal position of the bug? What was the input quantity we were looking at? I know Adam knows. What was the input quantity? Distance that the bug went? No. So what were we looking at? Say if we were going to graph this, we're going to put this on the horizontal axis here. Measure of an angle. Adam, is that what you're going to say? Measure of the angle. Right. But we want to be very specific. There's lots of angles we could define on this circle. We could start at different places. We could sweep counterclockwise, clockwise. So we need to be very specific. It's the measure of which angle? The measure of the angle swept counterclockwise from 3 o'clock position. We're going to beat that like a dead horse, okay? You're going to write that on your quiz today. You're going to write that on your quiz next week. The input into these functions is the measure of the angle swept counterclockwise from 3 o'clock. It's crucial. What was the output we were looking at? What was the output quantity we were looking at? So we transitioned. Yes, we did vertical distance on Wednesday, but then at the end we transitioned. We started doing, so horizontal distance. So we got to define what positive distance is. To the right of the vertical diameter. And what did we say our unit of measure was going to be? Okay, so radians is openness. Radians is openness. It never measures length, okay? Radians doesn't measure distance. Okay, right. But what's the most to the right we can get? No, in radius lengths. 1. So anything, most of these values are going to be between 0 and 1, or 0 and negative 1. So really, let's to help us keep the idea of what's going on, rather than saying radius lengths, we'll never have more than 1, right? It's going to always be, what, a fraction of a radius length. So let's state it that way and think of it that way, because, so we're going to say, we're going to output the horizontal distance to the right of the vertical diameter as a fraction of the radius length, because the most we can get is 1 whole radius length. Everything else would be 0.8, 0.2, negative 0.3, negative 0.95. Okay? So our unit is going to, so we're going to specify a fraction of a radius length, so that we're, I think, to be real specific, because we can never get radius lengths. We can never get more than 1, so it's never going to be 2 radius lengths or 3 radius lengths. So let's say it like it is, right? Let's say it like it is. It's going to be a fraction of a radius length. 1 is the most, a whole radius length. Okay, in the first quadrant here. So we had done the first quadrant. Let's do it again fast. What happens to the horizontal distance right to the right of the vertical diameter. Does it increase or decrease? Decreases from what to what? 1 to 0. The changes increase. So you can look at the top there, across the top. I'm showing you the changes for increments of angle measure of pi over 8. Do those changes increase or decrease?
Decrease.
Okay, most of you said decrease. Good. They decrease because their negative changes getting more negative. More negative. And so the rate of change then is decreasing. Graph is concave down. So it decreases, the horizontal distance decreases from 1 to 0. And those changes are decreasing. They're getting more negative. So we get a decreasing rate of change, concave down. All right, next quadrant. Does the horizontal distance increase or decrease? Decreases from what to what? So what's the horizontal distance right now? 0. And it will end up at? Okay, so it's going to decrease from 0 to -1. Changes. So watch those changes. Do they increase or decrease? Are they negative or positive changes? Negative changes. Because the quantity is decreasing, the changes are negative. Are they getting more or less negative? Less negative. So changes are increasing. These are getting less negative. So those changes are increasing. So the rate of change is? The rate of change is increasing, and the graph will be concave up. So can you imagine now in this next quadrant? The quantity is going to decrease from 0 to -1 at an increasing rate. So it'll be concave up. Draw it with your finger. Everyone draw it with your finger. And this is what you should have drawn. So when the angle increases from 0 to pi, the horizontal distance decreases from what to what? So as the angle increases from 0 to pi, the horizontal distance decreases from 1 to -1. At first, at a what kind of rate? Decreasing rate, getting more negative, and then at a increasing rate, getting more positive. The rate gets more positive. Okay, third quadrant. The horizontal distance will change from -1 to 0, and the change is positive or negative? There'll be positive changes getting more positive. Concave up, increasing rate of change. So you really have to keep track of this. We're measuring horizontal distance, but we're on this graph on the right, we're measuring it on the vertical axis, right? So what you see, the y-coordinate of these points is a horizontal distance on the circle. So this is harder to see than the sine curve. Last quadrant. As the angle theta changes from 1.5 pi to 2 pi, what does the horizontal distance do? Changes from? Right now we're at 0 horizontal distance. It'll change from 0 to 1. So then therefore those changes are positive or negative? Positive. Getting less positive. Therefore the rate of change is decreasing because the changes are decreasing. So the rate of change is decreasing. Okay, so our fan has a radius of 2.6 feet. But what we just did works for any circle. Why? Because we measured horizontal distance in what? Fraction of a radius length. Fraction of a radius length. So, maximum fraction of a radius length is 1 when the angle is equal to 0 and 2 pi. So at the start of the circle, And at the end of a full rotation, your horizontal distance to the right is 1 full radius length. You're as far right as you could be, and that's 1 whole radius length. Okay, at pi over 2, what's our horizontal distance? 0. When we get to an angle swept of pi, and that's there. All right, so this is -1. And then we go from pi to 1.5 pi. What's our horizontal distance? 0, and that's at 1.5 pi. And then back to 1. Yeah. I wrote down the y coordinate, not the x coordinate. Thank you. Okay, just like our vertical distance, this is special, universal. Universal because we're measuring this horizontal distance in fraction of a radius length. So this is the exact same graph you'll get for a circle the size of my ring as a circle the size of what's it called? So a particle accelerator, right? Those are huge. Like they build them so they want to collide particles. So they build these huge circles like miles in radius, right? But in both cases, it's the same because we're measuring in fraction of a radius length. And so this has a special name, which you learned in your homework last night, right? Input is angle swept counterclockwise from 3 o'clock. That's what that is. Measure of the angle. So this is a habit I'm trying to break over the last couple semesters. The input is not the angle. The angle is the object. What's the input? It's not the angle. The measure of the angle, okay? It's important because an angle is an object, like a hat or a table or a chair, whatever, or a runner or a bicycle, okay? The input is a quantity, and what's the quantity? The measure of the angle, okay? So theta is always the measure of the angle, and our output is horizontal distance right of the vertical diameter as fraction of a radius length, and the name of that is cosine theta. Students who understand the sine and the cosine, they understand it because they know, like the back of their hand, they know what the input quantity is and they know what the output quantity is. That's why we're going to drill it. If you understand what the input and output quantity of sine and cosine, you can apply that and solve so many problems, okay? So that's why we're going to work on that. It's understanding the input and the output, which makes you understand what's going on with sine and cosine. And so when you say, what is sine or what is cosine, you're referring to the output quantity. When I say, what is cosine, the answer is the horizontal distance, right? So you say, what is sine? What is cosine? That's asking, what is the output? What does it give? So whenever you have cosine, what is it? It is the horizontal distance right of the vertical diameter in fraction of a radius length. That's what cosine is. What do we need to give it to get that? Measure of the angle, so counterclockwise from the 3 o'clock position. So given a measure of an angle, a cosine is the horizontal distance right of the vertical diameter as a fraction of the radius length. Okay, so now we want to look at our fan. For our fan, what is the horizontal distance in feet to start with? Yeah, we had the radius of the fan was 2.6, so this is 2.6. And so at an angle swept of pi, that value would be negative 2.6. And suppose we are a quarter of the way up. So right back here, say. Oh no, say. Horizontal. Okay, and so say here, this is 3/4 of a radius length right here. Okay, so say, and this is where the bug is, right here. Close enough, okay? So somewhere around here, say this is 3/4, that says 0.75. How would you find the horizontal distance of the bug in feet? If I'm telling you that the bug here in the fourth quadrant is 0.75 of a radius length over to the right, then how would you find that in feet? 0.75 times 2.6 of 2.6. Okay, so if I wanted to do that as a function, I'm going to, so, and what is 0.75? That's the cosine, right? So if I wanted to write a second function, this one gives the horizontal distance in feet. Well, what did you do? You said you took the 0.75 times 2.6. And that 0.75 was the value of cosine. It was the fraction of the radius. So how would we write a function to get the bug's horizontal distance in feet? Yeah, so it's going to be, you're just going to take whatever fraction of the radius you are, cosine theta, you're going to take that fraction of 2.6. Whatever fraction you are of a radius to the right or left, take that fraction of 2.6, and then now that function outputs horizontal distance in feet. It should make perfect sense. That cosine is giving us the fraction of the radius, so we want that fraction of 2.6. So we multiply. Okay, so we've got our two functions that pinpoint the location of the bug, or a spot on the circle. Vertical distance is sine theta, horizontal distance cosine of theta. So let's go back and practice a little bit. Any questions on cosine or the graph that we get? Okay, so here's our bug. The fan is rotating, but we're gonna pause. We're gonna pause the fan, and I'm gonna say so estimate the value of sine and estimate the value of cosine for this position of the bug. Let's estimate all three. So estimate theta in radians. Sine theta, no calculators. This is estimation. It's based on your understanding. You're not calculating anything. This is based on your understanding of what these quantities are. So talk with your partner. Estimate the angle in radians, the sine, and the cosine. Go.
Yesterday, so I was late. Do you tell them about the classes?
I did.
Cool.
I'm going to say it again. Thank you.
Yeah. Sine is the vertical distance of the horizontal.
Okay. Estimating the angle. Estimating the angle. Lexi, what do you think? So I gave you some help there. Angle and radians.
About 5.2.
5.2. What do you think? The openness in radians is 5.2 from the 3 o'clock position. Yeah, because it's the same as that number is the same as how many radius lengths around the circumference, right? Radius lengths, and so the openness in radians is the same number as how many radius lengths, and it's something past 5, closer to, in between 5 and 6, but closer to 5. So estimate about 5.2. Sine theta. Sine theta. Estimate sine theta. Dad wants to do it.
It's around minus 0.85.
He wants minus 0.85. Agree? Disagree? First of all, minus or plus? We're below the horizontal diameter, so minus. He wants about 0.85. So 85% of the way down to the bottom. Something like that. Yeah, if you said negative 0.8 or negative 0.9, pretty good estimate. Okay, cosine theta. Yeah, Cody.
About 0.5.
He wants about 0.5. Positive or negative?
Positive.
Because it's to the?
Right.
It's to the right, so it's positive, and why 0.5?
Yeah.
So why are you saying 0.5, Cody?
Because it's about halfway of the horizontal diameter on the positive side.
Right, it's about halfway of the radius length, about half of the radius length. Okay, so really we're looking at this distance right here, we're saying is about 0.5 of a radius length. And then this distance down here is about negative 0.85. These two distances, what is another way to think about these two distances? And look at this. So you're saying go over 0.5 like this, and then go down negative 0.85 to get to this point. What is that? Those are coordinates, right? So this is like we're really finding this ordered pair. What's the x-coordinate? 0.5. Y-coordinate? All right, so this is another way to think of cosine and sine. Cosine is, if it's the horizontal distance, then cosine is the x-coordinate on the unit circle. That's another way to define cosine. Because a unit circle is based on a radius of 1, and we said the cosine was a fraction of the radius, so this works. So another way to define cosine is the x-coordinate on the unit circle. But we know the unit circle is not a specific circle, it's what? Every circle. The unit circle is every circle, because that 1 means any radius length, 1 radius length. Okay, that's what that 1 means. Okay, similarly, cosine then can be defined as y-coordinate on the unit circle. So we can write coordinates on the circle as cosine theta, sine theta. On the unit circle, or using radius length as our unit of measure. Coordinates of the point on the circle. So this is the coordinates of a point on any circle. As long as you know that you're measuring in fraction of a radius length. Okay, let's do this one more time. I'm going to do this one here. There we go. Okay, go. Estimate the angle measured in radians, estimate the cosine, estimate the sine. Everyone do it. So I'll give you some help there for the angle. And then I want you to estimate the coordinates in feet. All right, so estimate the coordinates in fraction of a radius length, sine and cosine, and then estimate the coordinates in feet. Matt, you got a question?
When finding the estimation of theta,
Yeah.
do you know if it's in pi lengths or do you want it in a decimal value?
No, I want to, for these estimations, I want decimals. So you're thinking about counting what? Counting radius lengths. When you get into those pi fractions, it's very easy to lose track of what it's really about. So, yeah.
So what's the radius length?
Oh, 2.6. Still the same fan. Same fan. Okay, Ramey. How about Ramey up there? Can you estimate what the measure of the angle theta is? Here. 3.8? Like it? You guys like 3.8 radians? Good, okay. And how about let's do in fraction of a radius first. What is, so the x-coordinate, is that sine or cosine? Cosine. So if we're estimating in fraction of a radius length, we're doing cosine first. Derek, what do you think for cosine, or the x-coordinate? What's that? Negative 0.6. I think we can do a little better than that. I think you got the right idea, but it's... Let's do a better... Yeah, so it's more, it's further left, right? It's further left than 0.6. More like 0.75, 0.7. Okay, what about the sine? Ashley? Y-coordinate? Negative 0.6 she wants. Yeah, this one's more closer to the middle. Okay, so now how are we going to get the coordinates in feet? So easy, right? Christopher? Yeah. So we want 0.7 of 2.6. We want that fraction of 2.6 to get how many feet it is. Anybody do that? So we're just going, all we're going to do is multiply. We want those fractions of a full radius, 2.6 feet. Negative 1.2? 8? And?
Negative 1 plus 5.
So that's in feet. And this is in fraction of a radius. So, which are the sine and cosine? The first ordered pair or the second ordered pair? First or second is sine and cosine?
First.
You better know this. I'm hearing some conflict. The first ordered pair, the top one or the bottom one? Which is the actual sine and cosine? Top one. The top one is the sine and cosine. Applies to any circle. For our particular circle, we can measure it in feet by taking those fractions of the radius in feet. Okay. Super important stuff because this sets the stage for like all of trig. Really understanding what sine and cosine. That's why we're kind of taking it slow and laboring it. Because if you can apply these principles when we add more ideas and throughout all of trig, then you'll be in good shape. Okay? So let's summarize. Okay? Quiz yourself. Quiz yourself. Can you write out full and complete, precise definitions for these two? Not for this, okay? Just ignore the specific case we got here. I'll just get rid of it. Generically. Okay. See if you can do it by yourself, writing it out precisely. Precisely. We did. Aiden, did you get the input of sine? Couldn't have said it better myself. Measure the angle, swept counterclockwise from 3 o'clock. Actually, the angle we can use any unit we want. We've been using radians, so that's okay. But for the input into sine, any degrees is fine, gradients, anything you want. Okay? What is the output? Benry, did you get the output of sine? What's that? Horizontal distance from the center. Not quite. Wyatt, did you get it?
I said it was the vertical distance from the point on the terminal side of the raised point angle with point on the circle from the x-axis.
Okay. So the vertical distance, you said above the x-axis? Measured in what? In radius lengths. Or we said fraction of a radius length, right? So it's vertical distance above the horizontal diameter. He said x-axis, that's fine. As a fraction of radius length. So saying radius lengths is okay, just as long as you know we're never going to get more than one length, right? So I'm going to emphasize fraction because radius lengths kind of makes it sound like you could get 2 or 3, all right? We're always going to get a fraction of the radius length or one whole radius length. Unit circle coordinate. X or Y? Y coordinate. All right. Input, cosine theta. Nick. Same input as sine. Same exact input as sine. Output of cosine. Divi.
Horizontal distance from the vertical radius towards the right.
Towards the right in what unit?
Fraction of radius.
That's it. Horizontal distance to the right of the vertical diameter as a fraction of the radius length. As a fraction of the radius length. Coordinate. X. Okay, so if you had some of those details off, make sure that you learn it. Get it precisely right. You got to get these precisely right. Every detail. Any questions? So sine is the last one on your quiz today or Monday. And then we'll do this whole thing again, like I said, next week's quiz. Okay, so let's put some stuff together here. Okay, so I've got, this is like a top view of a track, which is circular on the ends. The radius ends up being 36.5 meters from the center of this end of the track out to the first lane in the track. So the nearest lane is 36.5 meters. Okay, and so our runner is going to start at the starting line, and we're going to look at him running around the circle, the semicircle, in the first quarter of the first lap that he runs. So first I want to say that we're going to look at when he runs 22. So right here, he has run 22 meters from the starting line. He's run 22 meters from the starting line. I've got a series of questions for you, okay? You're not using your calculator until you get to part D, as in dog. So all you're doing in A, B, and C is you're writing expressions for that would give exact values. So you're going to write out expressions. You don't pull out your calculator until D. All right. So for number 1, he's run 22 meters. Work number 1 there, A through E, and I'm going to take attendance. Okay. Work together. Okay, let's talk through it. Hopefully you got through most of it. So, Natalie, how did part A go? So what is the corresponding angle measure in radians? How would you express it? She wants 22 over 36.5. People are nodding. Why? So why'd you do that? Right. Did you hear what she said? So we want to measure radians, we want to see how many radius lengths that we have. And she said 22, we want to find out what fraction then 22 is of the radius length to get how many radius lengths he's run. 22 over 36.5. Yeah, that was excellent. Good job. All right, so how about the vertical distance above the horizontal diameter? So we're looking at this right here. How would you express that in radius lengths then? How would you express that in radius lengths? Michael? Yeah. No, we're expressing it. We're not calculating anything. We must express it exactly. No estimates and no calculations. So how would you express it exactly? So we want vertical distance above the horizontal diameter. How can we get that? How can we express that exactly? What is that?
Oh, it's the measure of the arc length traveled in radius lengths in relation to the vertical distance above the horizontal axis.
Okay, but we need a way to represent this value of a vertical distance. Eric?
Do the radius times sine over, or not, or radius times sine, and then theta would be 22 over 36.5.
You want to multiply it by the radius? Sounds like you want to multiply it by the radius, is that right?
That's what I said. That's what I wanted to do.
So if I want the vertical distance above the horizontal diameter in a fraction of a radius, what is that? What is that? The vertical distance above the horizontal diameter and fraction of a radius length. Sine. That's what it is. That's sine. That's sine. Vertical distance above horizontal diameter and fraction of a radius length. That's sine of something. Because that's exactly what our definition of sine is. Sine of what? What's the input into sine? The angle of the measure swept counterclockwise, which we found in part A. So it's going to be 22 over. Doesn't make sense. It's going to be the sine of that angle measured in radians, 22 over 36.5. Now I want that vertical distance in meters. Tell me again. 36.5. Good. So it's now if I'm going to take that fraction of the radius, that fraction of 36.5. So we're putting everything together now. So that's part 2. So part 1 is the sine of the angle measure. And then part 2 of that is going to be, that sine is going to give us a fraction of the radius, so we want that same fraction of 36.5. Okay, so we want to express the horizontal distance now. We want to express this horizontal distance, first of all, as a fraction of the radius length. Let's see, Jennifer. So I want to express this horizontal distance right here from the vertical diameter as a fraction of the radius length. How would I do that? What is that? What is horizontal distance as a fraction of radius length? That's exactly what cosine is. So, cosine of what? The same angle. Cosine of the same measure of that angle. That's part 1. Part 2, if we want that in meters then? 36.5 times cosine of that. Okay, so let's see here. Let's find this one right here, just one of these. 36.5 times the cosine of 22 over 36.5. Did anyone get that? Anyone have that number?
36.5 or the
No, this whole thing. 36.5 times the cosine of 22 over 36.5.
30.07.
Why does that number make sense? 30.07 what? No, 36.5 is the radius. It can't be the radius. It's got to be a fraction of the radius, right? 30 points, it's meters. Why does that number make sense?
Taking that fraction of 36.5.
Okay. Looking at where the runner is. Does it look like he could be about 30 meters over? Yeah, because the whole way over is 36, and he's most of the way, right? He's most of the way. So 30 seems like a reasonable amount of 36 that he is to the right. Okay, there will be